Hello, Assalamu alaikum. In this video, we will discuss on fluid in motion, specifically under momentum analysis. So, in the previous videos, I've shown you how can we make use mass balance and also Bernoulli equations to measure or to calculate fluid properties at different points. For example, in a pipe flow, if you do have flow coming in out, we can calculate pressure, we can calculate velocity, mass flow rate and volume flow rate at both points. So we will continue in this video with momentum analysis. The conservation of momentum principle is the momentum of a system remain constant and the net force acting on it is zero, and thus the momentum of such systems is conserved. If you look at this equation, total force of a particle or a fluid that moving is equal to the mass of the particle or of the fluid times the acceleration or the movement of the particle, which is the momentum. You probably still didn't get what I'm trying to say, but let's have a look at a few pictures and videos. Look at this fireman. He's standing on the ground properly to hold the water hose. Or if he's not properly doing that, it could be like this. So what is actually happening to the water hose? Yeah, you're right. Because of the pressure of the water hose and the high velocity of the water going out from the hose, that makes the hose cannot stand still. Why the hose is wiggling and cannot stand still? And it's funny, but something scientifically that we have to figure out. That is why the fireman has to position himself properly to hold the water hose. Because of what? Because of the pressure of the water that due to the atmospheric plus the velocity of the water. This is a space shuttle that is lifted up due to the thrust that generated by the rocket engines as the result of the momentum change. And if you can imagine, the fuel and the gas generate a very high thrust to the engine that can lift tons, kilograms of rockets. Total F equal to M times A, right? Total force equal to M, the mass of the rocket, times A, acceleration of the rocket. The A here is generated from the engines due to the fuel supply to the engine, accelerated from 0 to 2000 meter per second. Just want to share with you a space shuttle launch.
Minus 90 seconds and counting. All systems are go. We're about 90 seconds from the launch of Space Shuttle Discovery. T-minus 60 seconds and counting.
Look carefully at the engine.
We are transferring to orbiter internal power at this time.
So interesting. You look carefully at the engine. Look at the smoke that running out from the engine. Yep, the position, the engine. Look.
And we have a go for auto sequence start. Discovery's onboard computers are
alright, they are igniting the engine.
T-minus 17 seconds and
yep, 7 seconds.
15.
See?
12. 11.
12.
10. 9.
Ignite the engine. Look at the thrust. Look at the thrust.
2, 1. Boost ignition and liftoff of the Space Shuttle Discovery
Alright, look a few more examples here. Look at this. This is kind of like the water hose again. For example, with high pressure and high velocity of the water that flowing from the hose outlet, definitely according to the mass balance, M in and M dot out, right? And then in the another video that I published after that, we have studied about Bernoulli equation, where we want to involve the pressure at both sides. We want to know what is the pressure here, what is the pressure here. Definitely they might have different pressure due to the size of the cross-sectional area and the position of the point. Another interesting point that I want to highlight in this video is how about in this control volume, big volume, we can make sure that this hose with high pressure of water running in it can be standing at the same position. The reaction force that can make this nozzle stand at the point. So if you look carefully, this is the tripod that hold the nozzle of the water hose, and definitely the hose have specific force that can stand properly to avoid the nozzle from wiggling or fall down. So our job in this video is to understand what is the reaction force that can anchor or that can hold the position of the nozzle. So we call in this analysis as momentum analysis. This airplane can move towards this direction. To move these tons of kilograms of airplane, definitely they require momentum analysis as well. Similar to this figure, if you look carefully, it will include the momentum analysis as well. I hope now you have an overview what we're trying to do with the momentum analysis. So as I mentioned earlier, imagine this like ball bearing here. So you can imagine a particle that have kilogram mass, and then this particle, we want it to be moving to this direction with specific velocity. Whenever this particle moving, definitely is not just a particle and the velocity. It's actually the combination of both mass times velocity. Okay, you can imagine something like this. For example, Prodwa Viva running at 120 km per hour, and you can compare with, for example, a truck with, let's say, 10 tons and running also at 120 km per hour. You can imagine if both of them involved in accident, which one will have worse condition? Definitely the lorry, because the lorry is not only 120 km per hour, the momentum of the lorry is 120 km per hour times 10 tons kilogram, compared to Kanchil, maybe 1 ton kilogram times 120 km per hour. So the impact of the lorry is worse than, worse is high compared to Prodwa Viva. So we go back to this equation. The net force of the particle that moving is equal to mass time acceleration. So mass, definitely we know mass of the particle, so usually it's constant, but acceleration is changing, right? So acceleration is changing, we put as dv at that direction over dt, or sometimes they put like this, F equal to m dot v. Okay, to have a better understanding why we say momentum analysis, it's not just momentum equation, but it's momentum analysis. If you look at this figure, this is a bending pipe that have a flow, water flowing from here and out here, right? So definitely velocity 1, velocity 2, okay, but it has a bending shape here with specific theta. If the velocity is high, the pressure also high here. The pressure gauge here, P1 pressure gauge is high. Definitely we need something to hold this bending elbow pipe at the position. Okay, let's try to go back to our previous chapter.
Okay, we have learned about continuity equation. So continuity equation is about mass balance, right? M dot in equal to M dot out. And then this one we have to assume it's incompressible. Again, when I say incompressible flow, what does it mean? It means the density is constant. Okay, so which means although continuity equation rho times A times area times velocity in equal to rho times A out times velocity out, because the rho is constant, you just take out. So definitely you can know area at point 1, velocity at point 1, you can know area at point 2, velocity at point 2 using continuity equation. And then after that we have studied about Bernoulli equation. I hope it's still fresh in your mind, in your brain, if you study. Okay, so Bernoulli equation, if you do have 2 points, remember what I always say that whenever you have 2 points you can have a set of Bernoulli equation, not 2 sets of Bernoulli equation. So P1 at point 1 over rho g plus V
plus Z2, right? So definitely we can calculate. Let's say we already used the continuity equation, then we can have V for both of them. We have V, right? Then definitely we can calculate at the pressure or at the, let's say Z1 is the reference line, this one becomes 0, right? Remember that? Okay. And then P2, they say this one is PATM. Okay. And then Z2 is given, then definitely we can calculate pressure 1, gauge pressure at point 1, right? Bernoulli equation. Okay, these two we provide you, I think maybe already 10 marks in the exam, and even a very good understanding about how can you understand the fluid or the transport of fluid in the fluid flow. Okay, another things that I want to highlight in this video is about momentum analysis. Momentum analysis says whenever you do have flow with specific pressure with specific velocity at point 1 and then running at, let's say, a nozzle, simple as like this one, you have water coming in and coming out, nozzle like that, you do have a momentum, a conservation of momentum that happen in both sides. And in this study we want to conservation of momentum that occur in the whole system and the control volume. Total force equal to total momentum at the out, yeah, minus total momentum at the inlet. How can we analyze this figure using this equation? If you can properly bring it out, is actually you can expand the total force that involved according to what? According to X and Y direction. If you look carefully in this figure, they give us something like this, the reaction force. The reaction force is something that we need to have it. For example, like remember, if you do have a hose like this, nozzle hose, then water flushing out or flowing out, and then you have a hose that going down, and then remember the tripod. Yes, the reaction force you need is for the tripod, so that the tripod can absorb the momentum that's produced by momentum at the outlet and at the inlet. So you can expand this to become according to the direction of the force. When we want to expand this equation, definitely we have to have a proper free body diagram, right?
We know that whenever flow coming in, so velocity 1, velocity out 2. Okay? And then pressure, how about the pressure? Pressure also same. Pressure don't have direction definitely. It's not, it has direction, but it's normal to the plane or to the surface, because pressure is not vector, it's scalar unit. Remember that? So P1 is coming in, right?
How about P2? P2 is it P2 also going out from the hose? No, it's wrong. Remember that pressure at point 2 is always go back to the system. So having this, we can draw it down, or we can write it down to become according to the direction.
So we always do this. It has to be analyzed according to the direction. So you analyze to the direction x first, x-axis. So x-axis, you do have f, get this one first, rx plus f to the right at point 1, p1, a1. Okay, how about at point 2? Okay, so p2 is actually in the opposite direction, right? If you draw carefully, become like that. Right, this is the figure. You do have P2 here. This one P2 hypotenuse. This one P2 sebelahan dia. This one is P2 yeah. And then you do have 30 degree theta. So what you want to have, if you want to have the resultant pressure in this direction. So basically minus P. So P2 cos, right? Cos 30 degrees here equal to, so we have finished in this part. We just finished this. Then we write equal to for this part. So for this part, at the inlet kilogram must be something kilogram inlet, right? V1. Sorry, we start with the outlet first, right? So V2, careful, V2, because at the outlet, cos, let's say 30 degree again. We use this one. Why it's positive? Because when you draw it down, when you draw like this, you want to have this, right? This one, V2. You want to have this. This is V2 that they give in the diagram. You want to have this, so definitely cos 30 degree. Tujuh belum habis. Belum is bersebelahan. Habis is hypotenuse. So cos 30 equal to
B bersebelahan. Alright. Over V2. So B is equal to V2 cos 30. So that's why I put V2 cos 30 here. Okay. Minus m dot v1. Definitely the same thing you have to do for direction, this one, z direction.
Z axis. So you do the same, f r z plus, do we have p1 a1 at, okay, let's write it down first, all of them. Minus p2 sine, definitely sine. Okay, remember this? Yeah. So sine 30, oh my, very bad handwriting. Sine 30 minus m dot v1.
So, like, this water jet strike stationary plane or stationary plate, normal to the plate. So, or we can analyze based on the water, based on the control volume that involved. So I hope when I say control volume, you still can imagine the chapter that we discussed before. I think in the video part 2. So this is the control volume. So the involvement of the velocity 1, pressure 1 here, okay, and then the cross sectional area 1. All right, and then what happened to the plates? So is the plate moving to the up down or moving to this side? We not really sure. So again, you can draw the equation again.
Total force that occur in the control volume is equal to the momentum of the water in minus water out minus momentum of water in. Okay, or sometimes you can put like this, out m dot v2 for example, or just v, or maybe v like this also can, minus in m dot v1 also can. Yeah. Okay, so if this analysis is, and then you definitely can have something here. For example, like you want to have you can expand this to become, let's say, according to positive, let's say you put direction, this is x direction, this is z direction, so you can have resultant force F. R is reaction or resultant force, okay? X, okay? And then do we have pressure to the right? Okay, let's say we do have pressure to the right, P1 here, okay? How about How about pressure at point 2? Let's just draw them down. P2, A2 equal to m dot out, m V2 minus m dot V out.
How about at y direction? Sorry, z direction. This is x direction. This is y, z direction. Do we have something with fz? No. Anything? No. Because the resultant force is not occur in both points. For example, point 1 is point V1, and at point 2 at the U also no. Nothing. So definitely we don't need this direction. So we only need this direction. Okay. And then second thing, you still can simplify this. Actually, in the previous example also can. V1 we do have V1. Sorry, this one should be V in. Direction should be V out. So V in, for example, if this plate doesn't move, okay, I want to say it doesn't move, so definitely V out becomes 0, so you can take out. V in, we have it, P1 and P2. P1 and P2, actually both of them open to atmosphere. We don't need them anymore, and definitely left us with only FRX and m dot V out, V in, sorry. Okay, let's move to an example. Oh, sorry, wait, not example yet. So when we do have flow, for example, running in this pipe from this side to and then flowing out at this side, you do have the bend degree. You have to include, as I show you in the previous derivation or the previous expression. And then whenever you involve theta, definitely for it could be cos theta or sin theta. And then if they ask you, or if you want to know the total force, the total reaction force in the system, you have to have the same mathematical equation, fx power of 2 plus fy power of 2 square root. And if you want to calculate, or if you want to know ratio between reaction force at the y direction, for example in this case y direction and x direction, we can use this one, inverse tangent fy over fx.